Hello friends, this is Pratik Kadam and we are back with second video of our lecture series Network Measures from subject Social Media Analytics. In last lecture or last video, we had seen the basics about network measures. If you haven't seen that video, I request you to please go through that video first. In that video, we had seen three questions. So, first question was, who are the central figures, that is, influential users in the network? So, to answer that question, we will be finding a centrality of a given network. The centrality of a given network will give us the central figures, that is, an influential individuals of a given social graph. So, what is centrality? Centrality defines how important a node is within a network. For example, suppose we have a huge graph of a social network and there are n number of users. Suppose a user A is having n number of friends. It means that he is having a huge number of reach. So we can consider that person as a central figure of the given graph. There are different ways of finding centrality of a given network. The types of centrality are: first, degree centrality, Eigenvector Centrality, Katz Centrality, PageRank, Betweenness Centrality, Closeness Centrality, and Group Centrality. While you are studying these types of centrality, I request you to please go through the sequence, because it is very important that you understand the sequence, because one centrality, the drawbacks of one centrality are overcome in the next centrality. So our first type is degree centrality. So its definition is a node with greater number of connections is considered important. For example, in a given graph we can see that V1 is connected with 8 other nodes. So you can see that V1 is having a higher centrality as per degree centrality. Equation for degree centrality in undirected graph is CD of V of I, that is ith node, is degree of that node. Basically, a degree of a particular node is number of connections to that node. Second, we have equations for directed graph. First is CD of VR equals to di of n, that is incoming edges. CD of VR equals to di of out, that is number of outgoing edges. And finally, the combined degree is di of in plus di of out. The main problem with degree centrality is we cannot compare a single user across different networks. For example, let us consider an actor, Hrithik Roshan. For suppose if he is having 100 friends on Facebook, but he is having 10 friends on LinkedIn. So I cannot compare his centrality among different networks, that is Facebook and LinkedIn. So for that case, we need to normalize our degree centrality. So there are three different ways of normalization of a degree centrality. First is normalization by number of nodes. So our example was an actor Hrithik Roshan is having 100 friends on Facebook and the total number of users on Facebook is suppose 1000. So his degree on Facebook is 100 upon 1000. And suppose on LinkedIn he is having 10 connections and total number of users on LinkedIn is 200, then we can say it as a degree of centrality of Hrithik Roshan on LinkedIn as 10 upon 200. So in this way now you can compare a centrality of a single user across different networks. Second method is normalization by maximum possible degree. In first case, our dividing factor was number of nodes. In this case, our dividing factor is a maximum degree. For example, on Facebook, there are 1000 users. Hrithik Roshan is having a degree 100. But if someone is having a max degree as 500, then for every user on a Facebook, while calculating his degree, we will be calculating as his degree upon maximum degree, that is 500. So in our case, degree of Hrithik Roshan is 100 and the maximum degree is 500. So the degree of Hrithik Roshan is 100 upon 500, that is 1 by 5. Third method is normalization by degree sum. So in first approach, our dividing factor was number of users. In second method, our dividing factor was maximum degree. And in third case, we are doing sum of all degrees of number of users in that particular network. For example, in our Facebook network, there are 1000 users. So we will be doing a summation of degree of all 1000 users, and that would be our dividing factor. So in our example, normalization of degree centrality of Hrithik Roshan would be 100 upon the summation of all degrees of 1000 users on Facebook. I hope now you have understood the concept of degree centrality and normalizing degree centrality. The concept of degree centrality is very simple to remember. The number of friends or the number of connections you have is degree of that particular user or particular node. So a second is Eigenvector Centrality. In degree centrality, we consider nodes with more connections to be more important. However, in real world scenarios, having more friends does not by itself guarantee that someone is important. It is just like suppose in your classroom there are 60 students and a particular student is having friendship with all other students, so his degree would be 59. But then you also have a professors, that is 10 professors for your department, and that particular professor is having friendship with 10 other professors. So can you say that the student having 59 connections is more important than the professor having 9 connections? Having more friends does not by itself guarantee that someone is important. So in eigenvector centrality, it tries to generalize degree centrality by incorporating the importance of neighbors. It is simply that your importance is decided by your neighbors or your friends. If you're having, it is just like your parents say, if you're having a good friends, then you have a great future, and if you're having a bad friends, then you have a bad future. So in this case, a centrality of particular node is decided by how important its neighbors are. So the equation for eigenvector centrality is lambda CE, that is eigenvector centrality equals to A transpose CE. Here A is a n by n matrix which gives us the connectivity between the two nodes. So in this given figure, we can see visually that node V2 is having three connections, that is V5, V1 and V3. Then V4 is having three connections, V3, V1 and V2. So in this case, both V2 and V4 are having different degrees, but the importance of V2 is transferred into V4, which gives V4 a more importance. Our next centrality is Katz centrality. A major problem with eigenvector centrality arises when it considers directed graphs. Centrality is only passed on when we have outgoing edges, and in special cases such as when a node is in a directed acyclic graph, centrality becomes zero, though edges may have many edges connected to it. In this case, the problem can be rectified by adding bias term to the centrality value. So, Katz centrality tries to balance this issue by adding bias term to the centrality value. So you can see that the equation of eigenvector centrality and equation of Katz centrality is somewhat similar. The only difference is that a bias term is added. So what exactly does this bias term do? Suppose if you are having a graph, a directed graph. So a particular node is having three incoming edges, but it is not having any outgoing edges. So that does not mean that that particular node is not important. But if we consider the equation of eigenvector centrality, in that case, that particular node gets a degree 0 because it is not having any outgoing edges. So to balance this, we are adding a bias term. So whenever such case arises, a bias term is added to that node so that no node is having a 0 importance. So our next type is PageRank. You might have heard this term many times because your Google search engine uses this algorithm. Similar to eigenvector centrality, Katz centrality encounters some major challenges. A challenge in directed graph is that Once a node becomes authority, that is high centrality, it passes all its centrality along all its outlinks. Did you get what I'm trying to say? In your previous approaches, suppose if you're having a friendship with a very important person, all its importance is passed to you. And it is not necessary always that a person known by a well-known person is always known. Did you get my point? So let us take one example. Suppose now in our college, if one of our students is having a friendship with suppose HOD ma'am and rest of the students does not have a friendship with HOD ma'am on Facebook. So HOD ma'am is having a very high centrality because she is considered as a very important person in college. So when we are using previous approaches, person, suppose Ajay is friend with HOD ma'am. So while calculating centrality using our Eigenvector Centrality or Katz Centrality, the entire importance of HOD ma'am is transferred to Ajay, which makes him a very high central node among other students. But this is wrong. So to mitigate this problem, one can divide all its values of past centrality by the number of outgoing links from that node, such that each connected neighbor gets a fraction of the source node centrality. Did you get this point? Okay. Suppose someone is having high centrality. So that person is having high centrality means he is having a higher degree. So our example was Ajay and HOD ma'am. So HOD ma'am is considered as a node having high centrality. This means the HOD ma'am is having a highest degree. Let us consider that HOD ma'am is having a degree 500. So now when HOD ma'am is transferring its degree to its neighbors, so rather than transferring entire 500 degree to Ajay, now as per PageRank approach, it will be passing 1 upon 500 degree to Ajay. So this helps in passing the degree equally to all the neighbors. So this is what a PageRank does. PageRank tries to solve this by passing fraction of node centrality, then passing complete centrality like previous approaches. The equation of PageRank can be seen. So if you see in Eigenvector Centrality, the equation was lambda C equals to A transpose C. In Katz Centrality, we are adding bias term. And in PageRank, we are adding D raised to minus 1. Here, D stands for the number of degrees of that particular node, so that a fraction part is passed to its neighbor. Our next type is Betweenness Centrality. Till now, we have calculated a centrality of a node based on its degrees and neighbors. But this is a very different approach to find centrality. So, another way of looking at centrality is by considering how important nodes are in connecting other nodes. In other words, we are measuring how central node V of i's role is in connecting any pair of node S and T. This measure is called Betweenness Centrality. So basically in this approach, what we are saying is, suppose we are having a graph. A centrality of node is decided upon how central it is, that is, every path from node, suppose V1 to Vz, is passing through that node V. You will better understand this with an example. So now we have a social graph with node 5, that is V1, V2, V3, V4, V5. So if we want to calculate a betweenness centrality of node V2, so what we are doing is, our formula was rho st of node Vi upon rho st. So rho st means all number of paths from S to T, and rho st V of I means all paths which are passing through the node V of I. So now we are calculating the centrality of node V2. So first path is V1 to V3. So number of shortest path from V1 to V3 is only one, that is V1, V2, V3, right? That is rho st. Now we are finding the centrality of node V2. So does this path pass through node V2? Yes. Hence it is 1 upon 1. Next, our source is V1 and destination is V4. Again it is similar. You can see that the shortest path from V1 to V4 is V1, V2, V4. That is, the number of paths are 1, shortest paths are 1, and it is also passing through V2, hence 1 upon 1. Next is V1 to V5. The number of shortest path here are 2, that is V1, V2, V3, V5, then V1, V2, V4, V5. So we are having two shortest paths, hence our denominator is 2. But both the paths are passing through node V2, hence it is 2 upon 2. Now let us consider V3 to V4. Look at this carefully because it will clarify your doubts. So now from node V3 to V4 we are having two shortest paths, that is V3, V2, V4. Next is V3, V5, V4. So total number of shortest paths are 2, hence our denominator is 2. But among these two paths, only one path passes through node V2, hence the numerator here is 1. Then for node V3 to V5, we are having only one path and it is not passing through V2, hence it is 0 upon 1, that is 0. Similar is the case with V4, V5. So we will be adding this all and multiplying it with V2. So you might be having question that why we are multiplying it with 2. The reason is we are dealing with undirected graphs. As it is undirected graphs, we can traverse V1, V2, V3 and V3, V2, V1. Hence, we are multiplying it with 2. So, in this case, the betweenness centrality of node V2 is 2 into 3.5, that is 7. Similarly, you can observe for the node V3. I'll give you some time for observation. So I hope that now you have understood what is betweenness centrality. So let's move forward further to our next type of centrality, that is closeness centrality. This is also a different approach. In closeness centrality, the intuition is that the more central nodes are, the more quickly they can reach other nodes. Formally, these nodes should have a smaller average shortest path length to other nodes. So closeness centrality is defined as Cc of V of I equals to 1 upon L of V of I, where L of V of I is node Vi's average shortest path length to other nodes. So let us clarify this with a simple example. We are considering same graph with 5 nodes, that is V1, V2, V3, V4 and V5. So to find a closeness centrality of node V1, we find a distance of V1 from all the remaining nodes. So the remaining nodes are, the distance from V1 is to V2 is 1, then V1 to V3 is 2, then V1 to V4 is again 2, and V1 to V5 is 3. We will be considering the shortest distance only. Then we are dividing it upon 4 because we have considered 4 nodes, and this whole is then divided by 1. So we get a closeness centrality of V1 as 0.5. Now let us consider for node V2. So distance from V2 to V1 is 1, V2 to V3 is 1, V2 to V4 is 1, and V2 to V5 is 2. So that is 1 plus 1 plus 1 plus 2 divided by number of nodes. And this whole is divided by 1, which we get 0.8. Similarly, we calculated for V3, V4 and V5. So after observing, you can see that node V2 is having a higher centrality among the given graph because from V2 we can go to all the nodes quickly compared to remaining nodes. So this is the homework for you all. So what we have to do, you have to do is, we have given you a graph, a social network graph having 10 edges. You have to find the node having highest degree using all approaches that we have studied till now, that is degree centrality, Eigenvector centrality, Katz centrality, PageRank, Betweenness centrality and Closeness centrality. Just to help you out, suppose you are to calculate a degree centrality of all these nodes. So in that case, the node V1 is having degree 1, node V2 is having degree 2. Similarly, you can calculate degree of all nodes. So after you calculate, you will see that node V3 and node V6 will be having highest degree, that is 1, 2, 3, 4. Similarly, V6 is having 1, 2, 3, 4. So as per degree centrality, the nodes having highest degree are V3 and V6. Similarly, you have to find a node having highest degree for remaining types of centrality. I request you to comment your answers below. Our last type is group centrality. It is not a different type of centrality, but earlier we have been considering a centrality of single node, but now we will be considering the centrality of a group of nodes. For example, suppose let us consider we have to find a group centrality of node v2 and v3, right? So in this case, when we calculate a degree of a group, in that case, degree will be 1, 2 and 3. So degree is 3. Similarly, when you are calculating a betweenness centrality, you will be considering v2 and v3 as a single node and then calculate a betweenness centrality. And the same applies with the closeness centrality. I hope you have understood the topic of centrality. If you have any doubts, you can comment below and I'll be happy to answer your queries. I hope you have enjoyed the second video of this lecture series. Have a great day. Bye bye. Thank you.